Well, it seems like every programming tutorial starts out having you write a simple program that just prints out "Hello World." And it's usually a pretty simple starting point because the programming language, in this case Python, and everything it's built on top of, does a lot of the work. But what if we don't have any of that? What if we just start with a microprocessor? And how do we get from this to printing "Hello World" on a screen of some sort? Well, this is the 6502 microprocessor, and it's a real classic. You can see from the date code that this one was manufactured in the third week of 1989. But the design for this has been around since 1975, and versions of this chip found their way into many personal computers and game consoles in the 80s. But believe it or not, even though the original design is 44 years old, a version of the 6502 is still being manufactured today. And in fact, for reasons I'll get into later, I'm going to use this modern version. And so here it is, and here's the datasheet for it, and you can see the datasheet's only about 30 pages long. But let's start taking a look at the pinout for this and start hooking up some of these pins to see what we can get it to do. You can see there's a description here as well for what each of the pins are. And if we flip back a couple pages, you can see a more detailed description of each of the pins and exactly what the function is. But let's start with the power pins. So VDD is positive power, VSS is the ground. So I'll put the microprocessor on a breadboard here. And VDD is pin 8, and that's our positive power supply. So I'll connect that to the positive power rail of our breadboard. And then VSS is pin 21, so that's ground, so I'll connect that to the ground rail on the breadboard. So at this point, if we connected 5 volts here to our breadboard, it would power up the microprocessor, but it's not going to do very much because we need to connect some of these other pins. And if we look at these pins, some are going to be inputs and some are going to be outputs. And the outputs I'm not going to worry about too much just yet. So for example, pin 1 here is vector pull. And we can see here that it's an output and it indicates some particular condition. But if we don't care about what it's outputting, then we don't need to connect it to anything to get the processor to work. But that's not the case for pin 2. Pin 2 is the ready pin, and you can see that's an input. And so it is going to matter to the processor what we hook this to. And in fact, the ready signal indicates whether the processor is going to run or halt. And so if we want it to run, we need to hook pin 2 to 5 volts. And so now I'm basically going to do the same thing for the rest of these pins. Any pins that are inputs, I want to hook to something reasonable that'll get the microprocessor to run. And so I'll just go pin by pin. So pin 3 here, phi10, that's an output, so I'm not going to worry about that. Pin 4 is the IRQB, that's interrupt request, and that's an input. And bringing it low will trigger an interrupt, so I'll just tie it high for now so that we're not triggering an interrupt. Pin 5, MLB, that's a memory lock, that's another output, so I'll leave that alone. NMIB, that's the non-maskable interrupt, so just like the regular interrupt request here, bringing it low triggers the non-maskable interrupt, so I'll tie that high as well so that we're not triggering that. Sync is another output, so I won't connect that to anything yet. VDD, of course, we already have that connected. That's our positive power supply. And then we have this A0 all the way around through A15. And these are the 16 address lines, and so they're actually all outputs. So I'll leave them unconnected for now as well. And then next we have these 8 pins here, D0 through D7. That's the data bus. And these can actually be inputs or outputs. And in fact, the next pin here, this RWB, pin 34, that's an output signal that tells us whether the processor is using the data pins for input or for output. And so if this read-write signal on pin 34, if that's high, then that means the data bus pins are inputs. And if that's low, then it means the data bus pins are outputs. So for now, I'm going to leave these unconnected, but we will need to come back here and connect something to these. So moving on, NC is no connect. So that means we actually shouldn't connect anything to that. So that's easy. Pin 36, BE, that's bus enable. And that's another input. So the bus enable signal needs to be high in order for the processor to put anything out on either the address bus or the data bus. So basically we want that to be high all the time. So I'll connect pin 36 to 5 volts, so it's high. And then we get to pin 37 is phi2, and that's the clock input. And like all computers, we need a system clock in order to provide timing for the microprocessor. And the original 6502 used a 1 megahertz clock, but this modern version that I'm using is a bit more flexible, so we can actually run it up to 17 megahertz. An easy way to provide a clock input is to use one of these crystal oscillator modules. This one, for example, is 10 megahertz. And so if we just connected ground and 5 volts here, it would output a 10 megahertz clock that we could then just connect directly to pin 37 up here. But in this video, I actually want to run the clock much slower so we can really see what's going on. So I'm not going to use this. Instead, I'm going to use this clock module that I built in some previous videos for my other breadboard CPU project. And if I power this up, you can see it gives us a clock pulse that we can actually adjust. So I can slow it down or speed it up. And we can also halt it and then single step it so we can get nice single clean clock pulses that way. And if you want to know more about how this works, I've got several videos that walk through it all and explain how the 555 timer that we're using works in astable, monostable, and bistable modes. So, check that out there if you're interested. But in any event, I'll connect this clock here to pin 37, which is our clock input over here, and let that clock run. And this is where it's actually really important that I'm using the modern static version of the 6502, because the datasheet here says that phi2 can be held in either the high or low state, and it'll preserve the contents of internal registers. And that's actually not the case with the original 6502. If the clock for this stopped or got too slow, it wouldn't work. You'd lose the contents of the internal registers. But here, because we're using this modern, the W65C02, which is a fully static design, we can stop the clock and we can single step it, which is really nice. And so that's the clock, pin 37. And so just for the last couple of pins, pin 38 is set overflow. And that's an input, but the datasheet basically says it's not recommended to do anything with it other than just tie it high. So that's what I'll do. And then pin 39, phi20, that's an output, so we won't do anything with that. And then pin 40 is the reset signal, which normally needs to be tied high when the processor is running. But we'll want to be able to bring it low to reset the processor. So what I'll do is I'll tie it high through a 1K resistor. So now it's tied to 5 volts through that 1K resistor. But then what I'll do is I'll add a button here. And then I'll connect the other side of the button to ground. That way, when we push the button, that will short this pin to ground and trigger a reset. Otherwise, if we're not pushing the button, it won't be shorted to ground and it'll be tied to 5 volts through that resistor. And so that ought to take care of pretty much everything we need to set up just to get the processor to do something. And so I've connected power across here so that if we just plug in 5 volts over here, then that should power up everything. And of course, we've got the clock running. So if we hit the reset button here, that should reset the microprocessor, and now the processor is maybe doing something. But what is it doing? How can we figure out what's going on here? Well, of course, we still have a bunch of output pins here that we haven't hooked anything yet. So we could hook up some of those output pins, to drive some LEDs and see if they're doing anything. So let's give that a try. I'll add a couple LEDs here that we can use to look at some of the outputs from the microprocessor. And then I'll connect a few of the address lines to them. And so I'm just connecting up the first 5 address lines, A0 through A4. And then I'll connect the other side of the LEDs to ground through 220 ohm resistors. And okay, so something's going on here. The processor's doing something, but I'm not really entirely sure what. So how can we get a better picture of what's going on here? Well, we could certainly add a bunch more LEDs to look at the rest of the address lines and maybe look at some of the data lines and maybe some of these other output signals. But that's a lot of LEDs, and it's going to be really hard to keep track of everything going on, especially if we're trying to sort of figure out kind of a pattern over a period of time. Yeah, but there are tools we can use to make analyzing a digital circuit like this easier. So for example, we could use a logic analyzer, which has a whole bunch of inputs, and the one I've got has 16 inputs here. And we can hook each of these inputs up to a separate signal and use the logic analyzer to capture what's going on over a period of time so we can analyze it. And then if we capture while the circuit is running, what we get is a display like this that tracks each of the signals. So here we can see all of our address lines and, maybe try to figure out from this, what's going on. And so logic analyzer is great, especially for a high-speed circuit with a lot going on. But for something lower speed like this that we can actually run, and we in fact want to run pretty slow, I think a logic analyzer is overkill. I think a much better and definitely less expensive tool is actually just an Arduino. Because if we want to monitor what these address lines are doing, we can just hook them up to inputs on the Arduino and have the Arduino just read whatever's on each of these pins. And, especially something like this, Arduino Mega, it's got, something like 50 digital inputs. So way more than the 16 inputs that we have on a nice logic analyzer like this. The drawback, of course, is, the Arduino is much slower. We can read millions of samples per second with a logic analyzer, but that's fine. If we're running our clock slow enough, that's not going to be a big deal. So if we get the logic analyzer out of the way, and also get these LEDs out of here, then what I can do is hook those 16 address lines up to 16 of the digital I/O pins on this Arduino. So just like the logic analyzer, the Arduino can then keep track of, what each address line is doing. So I'll connect this ribbon cable with 16 connectors over to 16 of the digital inputs on the Arduino. And then the other end I'll connect to the 16 address lines. And I'll also need to connect the ground, of course. And so once I've got the 16 address lines then connected into 16 digital I/O pins of the Arduino, then we'll need to program the Arduino to read each of those address lines and show us what it's doing. Okay, so I'll start by listing out the 16 pin numbers that I used. And I guess I could use any of the digital I/O pins on the Arduino, but these are the 16 pins that I used for the address, starting with A15, which is on pin 22, and going to A0, which is on pin 52 at the bottom. Then in the setup function, I'll loop through all 16 pins and set the pin mode for each to input. And so what that does is just sets all 16 of these pin numbers here. It just goes through all 16 of them and sets them to input. And then in the loop function here, I want to go through each of those same pins again. And here I want to actually read each bit. I think digital read returns a Boolean, so if I want a 1 or a 0 here, then I can say if it's true, I want a 1, otherwise I want a 0. And then what I can do is I can assign this to an integer. And then after we have that 0 or 1, we can print that to the serial monitor. Then after we've printed all 16 bits here, then we'll print a new line. So this ought to read all 16 bits from pin 22, which is address 15, all the way down to address 0, and print each bit in order, and then print a new line. It'll just keep doing that. And of course, in our setup, we need to initialize the serial port up here. So we'll initialize the serial port to 57600, which is just the standard speed. Okay, so this ought to continually read those 16 bits and print them on the serial monitor. So let's give it a try. I'll connect the Arduino up and then compile and upload the sketch. There we go. Now if I open up the serial monitor, hey, we're seeing some numbers. And so it looks like we're getting something, but how do we make sense of this? You know, it looks like it's just kind of spewing a bunch of 1s and 0s that are changing, you know, maybe on every clock pulse, or maybe it's every other clock pulse. It's actually kind of hard to tell. In fact, actually, that's a good question. You know, it'd be really helpful if we can correlate what we're seeing here from the Arduino with the actual clock pulses. You know, fortunately, we've got lots more I/O pins here on the Arduino, so let's look the clock pin up as well. So I'll connect the clock to pin 2 here on the Arduino. And I'll close the serial monitor here. Then I'll define clock to be pin 2. And then in the setup function here, I'll set the pin mode for clock to input. And then rather than reading the clock pin and displaying it like we're doing with the address lines here, what I'm going to do is I'm going to have the clock pin trigger an interrupt. So in the setup here, what I'll do is I'll attach an interrupt to the interrupt for the clock pin. And actually only some of the pins on the Arduino support interrupts, but pin 2 is one of them, so we should be okay here. And then what we'll do is we'll have the interrupt call a function called onClock. And we'll do that on the rising edge of the clock signal when it transitions from low to high. Then what I can do is I can create that onClock function here. And then if I move all this stuff from the loop function into the onClock function, you know, instead of just constantly looping and printing out the address pins, it'll just read and print out the values of the address pins once per clock pulse. And so my Arduino loop function actually doesn't do anything. The only time we do anything is when we get a clock pulse, and then we just print the address once. So let's give this a try. We'll go ahead and upload that. And I'll bring up the serial monitor. And now we're getting just 1 line per clock pulse. So now if I stop the clock, you can see it stops, and then I can actually single step it. So that's great, but you know, the actual data we're getting still doesn't make a whole lot of sense, at least not to me. So let's try looking at a few more pins. You know, so we're looking at the address lines here, but you know, we could also look at the data bus, right? There's another 8 bits here that represents the data bus. So let me hook those pins up to the Arduino as well. Okay, so now what I've got is I've got the odd pins here from 39 to 53 are now monitoring the data bus, going from D7 down to D0. All right, so now that I've got the 8 data pins hooked up, we'll go back to the Arduino, and I want to kind of do the same thing. So first I'll list out all of the pin numbers for the data bus. Okay, so it's going to be 39 through 53, it's the odd numbers. So those are my data pins, and then I'm going to initialize them the same way. So I'm just going to loop through all the data pins. Of course, instead of 16, there's 8 of them, and they aren't the address pins, they're the data pins. So this will loop through and set the pin mode for each of the 8 data pins to input. Then in the onClock function down here, I'm going to kind of do the same thing. So I'm just going to copy this loop that prints the 16 address lines, and we'll duplicate that. And we want to print the 8 data lines. So there we go. And then between these two, we'll just print a few spaces. The other thing I can do here to make it easier to sort of interpret what's going on is instead of just printing out the binary ones and zeros like we are, we could print the values in decimal or actually in hexadecimal. So to do that, what we need to do is compute the value that we're reading. So what I'll do is at the beginning of here where we read each address, I'll start with the address equal to 0. Then each time we read a bit, I'll shift whatever address is over 1 bit and then add the bit that we just read. So now after we read all 16 bits, this address variable will have the address value in it as a number. And actually our address isn't ever going to be negative, so let me make this unsigned. So there we go. So when we get to the end of this loop, our address will equal whatever the address actually is. And then I can do the same thing for the data. Start with data equal to 0 each time, and then each time we read a bit, we'll shift the data left 1 bit and add the new bit. So by the time we've read all 8 bits, the first bit will have been shifted to the left 7 times. So now that we've got the address and data as integers, we can just print them out. So I'll use sprintf so I can format them to a string, and I'll call that string output. And then I'll print the address as a 4-digit hex number, and the data as a 2-digit hex number. So address and data. Then I want to actually print out the formatted output. And of course I actually need to define output up here. So just make that a character string. 15 should be long enough. Okay, and then one last thing I want to add here is remember that the 8 bits that we're looking at, the 8 data bits, can either be inputs or outputs. And that's actually what the next pin here indicates, this read-write pin. So that's this pin here, indicates whether the data bus is either inputting or outputting from the processor. So if this read-write pin is high, then it means the processor is reading from the data bus, and if this is low, then it means it's writing to the data bus. So it'd be good to keep our eye on this read-write signal as well. So what I'm going to do is I'm going to hook that up to pin 3 over here. Then in the code, I'll define read-write as pin 3. Then in the setup function, we'll set the pin mode for the read-write pin to input, so the Arduino can read and tell us what that pin is doing. Then when I print everything to the output here, what I want to do is also print out what that read-write pin is doing. So what I'll do is add a character to our output string to indicate if the processor is reading or writing to the data bus. And then the actual character will be based on what the Arduino reads from that read-write pin. And this digital read returns true or false. But we can say that if it's true, print an R, since that means the processor is reading from the data bus. Otherwise, if it's false, print a W, since that means it's writing to the data bus. Okay, now let's run this and see what happens. And it looks like I missed a comma here. Let's run this and see what happens. There we go. Looks like that's working better. I'll bring back our serial monitor. And I guess we need to start our clock. And there we go. Now it's doing something. Okay, so it looks like it's doing something, but it's not really clear to me what it's doing exactly. You can see the address is sort of jumping around. The data is jumping around to different values. Sometimes it's reading, sometimes it's writing. But honestly, I'm not really sure what's going on here. But one thing that is kind of interesting is you can see at least sometimes it is trying to read from the data bus. So each time we see this read here, it's essentially treating those 8 data pins as inputs, right? So it's actually treating these pins here as inputs, and there's really nothing connected to them other than the Arduino, and the Arduino is just monitoring them. So there's nothing connected to these 8 pins that's driving them. So whenever the processor tries to read data from those pins, it's really just going to get garbage. So if the processor is just kind of reading garbage whenever it reads from those data pins, I guess I would sort of expect it to behave kind of randomly. But one thing we could try is we could actually try connecting those data pins to some kind of predictable signal so that the processor isn't just reading garbage. Let's actually try that. So what I'll do is I'll tie each data bit here either to ground or to 5 volts. And actually what I'm doing is I'm tying each to either ground or 5 volts through a 1K resistor. That way when the processor is reading from the data bus, then it'll see whatever voltage is on the other side of that resistor, either 5 volts or ground, so interpret as either a 1 or a 0. But if the processor outputs something, then it'll be able to drive the output either to 0 or 5 volts, and then, worst case, there'll be like a 5 volt difference across that resistor, which is no big deal. So in other words, these resistors that I'm adding here are just kind of setting a default value. But, if the processor outputs something different, then, no big deal. And so now I've hooked these resistors to either ground or 5 volts in a particular way so that the data that the processor is going to read is going to be 11101010. And, I picked that particular pattern for a reason, as you'll see in a minute. But anyway, let's take a look at what it's doing. Yeah, so right away, you'll notice it's behaving a lot more predictably. So, a couple things you'll notice. One, it's always reading, or it seems to be always reading. And of course, what it's reading is EA in hex, which is the 11101010. That's the value that I hard-coded with those resistors. So it's reading the value that I set there. But it's always just reading. That's all it's doing. It's not reading and writing. And the address is behaving much more sanely, I guess. You can see the address is just counting, right? So it's, FFFE, F, 80, 81, 82, 83. So it's just counting up in hexadecimal, obviously, but it's just counting. So something about providing that hard-coded input is helping it behave much more predictably. So let's take a closer look at what's going on here. So remember, I've got this reset button here, and when I press it, you'll see something happens here. The addresses kind of jump around a little bit, and then it just kind of settles down into that same pattern that we saw before, where it's just counting here in hexadecimal. And so this is kind of interesting that it seems to have this sort of behavior where it's counting, but then if I hit reset, you'll see it kind of goes through some other interesting little behavior, and then it just settles right back down into that sort of hexadecimal or binary, whatever, counting behavior that it was doing before. So reset is doing something. And so now if we look at the datasheet, there's actually a description of what the reset signal does. It says it'll initialize the microprocessor and start program execution. Okay. And it says when a positive edge is detected, there'll be a reset sequence lasting 7 clock cycles. So let's take a look at that. I'll hold reset here and then stop the clock. And then what I'll do is clear the monitor output here. And so the reset sequence is 7 clock cycles, so let's do that. Let's pulse the clock 7 times. 1, 2, 3, 4, 5, 6, 7. And so that's what we get. So that's apparently the reset sequence. It's not really clear what it's doing, but I guess it's going through its reset sequence, whatever that might be. So let's look back at the datasheet, right? So it says there's a reset sequence lasting 7 clock cycles. Then it says the program counter is loaded with the reset vector from locations FFFC, a low byte, and FFFD, a high byte. And it says that's the start location for program control. So let's keep going here. So we got the first 7 steps here, and that's sort of the reset sequence. I'm not really sure what exactly it's doing there, but presumably it's resetting itself. So let's advance the clock one more time. And now what we see is it's reading at address FFFC. So it's setting the address to FFFC, and it's reading. And so that's interesting because we just saw FFFC as being something that the reset would do. So it would read from FFFC, and then it would read from FFFD. And it said that would be the start location for program control. So let's see what it does next. So next it's going to read from FFFD. And so it's doing these 2 reads, right? FFFC and FFFD, and it's reading from the data bus. And each time it reads from the data bus, it gets EA, right? Because that's just what I've hardwired in there with those resistors. And so the data sheet says that the program counter is loaded with that. So inside the processor, there's a program counter register, and now it's loaded with a low byte of EA, because that's what it reads, because that's what it always reads, and a high byte of EA. So in other words, the program counter is EA. And then it says this is the start location for program control. Okay, so the start location for program control in our case is EA. So we've gone through this 7 clock cycle reset sequence. We've read the reset vector from these 2 locations, FFFC and FFFD. And so on the next clock pulse, it's actually going to start running the program. So let's see what happens. So if I advance the clock once, well, look at that. Now the address is EA. And that actually makes sense because the processor is just starting to execute a program. And during that reset sequence, we saw that EA was going to be the start location for program control. So now the processor is actually trying to run a program. And so it goes to address EA. It sets its address pins to that address, and it reads from the data bus. And so what it's doing is it's saying, okay, this is the first address of a program. So let me try to read an instruction at that address. So it sets the address and it reads. And so in this case, when it reads, it gets EA again. And so now it's going to try to interpret EA as an instruction and actually try to execute it. So of course that raises an interesting question, which is, how is the processor going to interpret EA as an instruction? Well, if we look in the datasheet, we can find this opcode matrix. And then we can see if the most significant digit is an E, and then the other digit is an A. We come over here and we find out that the opcode for EA is no op. And that's the instruction for no operation. So EA is the opcode for no op, for no operation. So basically the processor is going to do nothing. And so if we pulse the clock again, we can see after presumably doing nothing, the address increments, and it reads the next instruction in our program, I guess, if you want to call it that, which of course is another no-op. And if we just keep pulsing that clock, this is going to go on forever. And it's just going to keep reading no-op instructions, advancing to the next address, reading a no-op, and so on. Although one thing you might notice here is that actually it looks like I have to pulse the clock twice for it to advance to the next address. So it almost seems like the no-op instruction is taking 2 clock cycles to execute. And in fact, that's right. If we come back to the opcode matrix table here, you see the no-op has this little I underneath there. And that means that's the addressing mode. If we flip back a couple pages here, you can see in the addressing mode table, I is implied. You can see for the chip we're using, instructions that use that implied addressing mode take 2 clock cycles, or the instruction time is 2 clock cycles. And so if I just let this run, that's what we see. We see it just reading that EA, we see it reading that no-op instruction, and every 2 clock cycles it advances to the next address and reads another no-op instruction, and just keeps doing nothing forever. And so hopefully you can see that the microprocessor here is initializing, and it's trying to fetch and execute instructions. And so, right now we're not able to feed it instructions from anything other than, literally hardwiring the no-op instruction. But in the next video, I'll hook up a ROM chip that we can program with some different instructions that the processor will be able to fetch using different addresses, and see if we can use that to actually write some sort of hello world program. Now, if you'd like to follow along with these videos and build your own simple computer with the 6502 microprocessor, I've gathered all the parts that I'm going to be using into this series into a kit. And so this is what I'm going to be building towards in these videos, something with a simple display and a couple buttons, and then I'll walk through programming a game or something in assembly language. There's obviously a lot more stuff in this kit than what I covered in the video. I've got RAM and ROM chips and all sorts of input and output stuff, but I'll get to all that in future videos. So for more information about getting one of these kits, check out my website at eater.net/6502. There's also some information there about a few other things that you'll need that I didn't include in the kit, like an EEPROM programmer, which you'll definitely need in order to program the computer, as well as a kit for the clock circuit that I used in this video and the Arduino Mega that I used in this video. Anyhow, more information on all of this at eater.net/6502, or click the link that's somewhere on the screen. And as always, thanks to my patrons who make putting these types of bigger projects together possible.